matter without quasiparticles.
Okay, so there'll be no topology in my talk, unlike the conference title, but there will be conformal invariance and some geometry. So with that apology, let me go ahead and begin. So a very elementary introduction, probably not necessary for the physicists here, I think. So if you look at our theory of condensed matter states, the most successful theories that we've worked on for many years are based on two principles. One is the principle of just writing down a many-body wave function as the product of single particle states, as in the theory of metals. And then for the excitations, there's the idea of quasiparticles. You create, say, in a metal particle and hole pairs, which remain well defined even in the presence of interactions between the excitations. And these quasiparticles then lead to what you can call the Boltzmann-Landau theory that helps us define various experimental properties. So of course, almost everything we've heard about in this conference is about systems where the first is not true. These complicated states with topological order, like the fractional quantum Hall state, are definitely not product states of single particle wave functions. But the second assumption, that there are quasiparticles, still holds and was in fact the underlying assumption behind almost every talk we heard. You take these quasiparticles and braid them and they have interesting properties. And these quasiparticles in the end are an almost complete description of the low energy Hilbert space of the theory. So the quasiparticle concept in some sense is more powerful and also applies to rather more complicated states. But suppose we ask that we are interested in quantum states where even that is not true, then the number of examples where this works is actually quite small. And in some sense, there's only really two examples. And the first one is what I'm going to focus on, are conformal field theories. In spatial dimension d equals 1, which is by far the most thoroughly studied case, called CFT2s, some aspects of quasiparticle physics still remain, and so that's not of sufficient complexity for the issues I'll be addressing. So the simplest examples really turn out to be conformal field theories in dimension d greater than 1, and that will be the subject of my presentation. There are also other examples which a lot of progress has been made in the last few years, which are metallic states, which I won't say anything about today. Okay, so this is what I'm going to focus on, just conformal field theories, actually particularly in 2+1 dimensions. I should also mention that the new work I'm going to present today is in collaboration with Immanuel Katz, who's a particle theorist at Boston University, William Krempa, who's a postdoc at Perimeter, and Eric Sorensen, who's done the quantum Monte Carlo studies. Okay, so here's the outline. So let me first define what a conformal field theory is, and then we'll talk about its dynamics, and we'll think about the dynamics, in this case really finite temperature dynamics. We have a finite density of excitations in three different ways, from the Boltzmann approach, from the operator product expansion, and I hope to get to this. This is from the holographic gravitational point of view. Okay, so let me begin, since this is a math conference, by at least being rigorous for one slide. So this is a definition of a model that many physicists would love to study, and it's a very simple model. It has bosons that can sit on the sides of a square lattice, let's say, and these Bose operators obey this commutation relation, B and its Hermitian conjugate. And this is the boson hopping term. Bosons can hop from site to site with the matrix element T, and then there's repulsion between the bosons of energy U. So that's it. So formally speaking, this is a full definition of the model. This is all you need to know, and you should be able to now work out its Hilbert space and in the limit, of course, of an infinite system size. and then predict all kinds of time-dependent properties. So that's, of course, a tall order, but this is just to emphasize that a very, very simple model, simple to state anyway, has an incredible amount of richness. Okay, so there's one dimensionless parameter, or one more thing I should say. I'm going to focus on the case where the number of bosons, total number, which commutes with the Hamiltonian, is an integer multiple of the number of sites, in particular, just equal to the number of sites. So there's one dimensionless parameter that's u over t. When u is very large, we can write down the ground state simply. It's just one boson on every site. They repel each other, so that's the ground state wave function. And then we can also identify the low energy excitations. You can take a particle from somewhere else and add it there. And then this extra boson can hop around and that's your quasiparticle. So this is a state that does have a quasiparticle, which will be a boson, won't have any fancy topological statistics. But you can also remove a particle, and so you have a negatively charged antiparticle, which can move around. Okay, so that's the ground state for u much bigger than t, just an insulator. On the other hand, for u much smaller than t, you have a very different ground state, which you can write this way. So this is, notice that's different from this in the structure. Here you're putting the bosons in the zero momentum state, and all of them in the same zero momentum state, so that's the Bose-Einstein condensate. And when you expand this out, you get states with lots of number fluctuation between the sites. So what we know is that in the limit of infinite system size, there's a very sharp phase transition at some critical value of u over t between the superfluid state and the insulating state. And this is characterized by a broken symmetry, if you wish. This is the Bose-Einstein condensate, where the zero momentum state, which I'll call psi, behaves like a classical number and has a macroscopic number of particles, and in the insulator where that's zero. Now in the vicinity of this point, and here I'm skipping some steps, we can write down an effective theory for the low energy Hilbert space. And it turns out the most convenient way to think about it is in terms of a quantum field theory. And so this is the quantum field theory of a complex scalar in 2+1 space-time dimensions, where the mass, the bare mass, this mass of the scalar here vanishes at the critical point, and there's some self-interaction, four-body term between the scalar. So what we know with a high degree of certainty is that for the model as defined, although there's no proof of it, is at this point is a conformal field theory. So it's in fact a conformal field theory associated with first studied by Wilson and Fisher, where under renormalization group analysis they showed that this coupling u goes to a fixed point value which we call u star, and at that point the theory is conformally invariant, although they didn't show that, we know that today, and then its properties are what we want to study. Okay, so my discussion so far is just a laboratory for finding a system which is formally but not rigorously proven as a conformal field theory, but it's clearly a very well-defined model, and a very precise claim is made for the nature of the quantum state at this point. So this will turn out to be the point at which there are no quasiparticles. There are quasiparticles on either side, but at that point there aren't. Okay, so what are conformal field theories? So this is so these are field theories where expectation values base nice properties on a conformal transformation, and they have some basic properties which perhaps are familiar, which look similar to what is also true in 1+1 dimensions, but the set of conformal ordered entities are now not as strong as 1+1, and so the theories have a much more complicated structure. So the CFT is characterized by operators which have a scaling dimension, and these operators have, can be diagonalized to have only diagonal expectation values when in pairs, and then they obey something called the operator product expansion, which is kind of implicit in many of the things we heard about yesterday. And there we were talking about fusing quasiparticles. Here you're fusing operators, and each operator does not create a particle. It creates some complicated set of excitations which don't have a particle-like nature and which can't be separated from each other. Nevertheless, you can still ask the question, what happens when two operators, as in a correlation function, approach the same point, and then they fuse into a third operator, and this coefficient is called the operator product expansion coefficient. So now, in principle, at least all local correlation functions of the CFT can be built up from a table of these scaling dimensions delta A and these OPE coefficients FABC, and you can view that as some data that define a conformal field theory. Of course, you can't just pick arbitrary numbers. There's only a very special set of values that people determine usually through numerical analysis, which are allowed and known to exist for certain models. In particular, for this O2 Wilson-Fisher CFT, a lot is known about the values of these numbers. They're almost certainly all irrational, but again, there's no proof of that. Okay, so then just like in CFT2s, there are a certain set of operators which have which are very important and which have certain nice properties. And these are the stress energy momentum tensor, which we call T mu nu, and any conserved current J mu. So in 1 plus 1 dimensions, you know that the energy momentum tensor, first of all, has this holomorphic factorization, and it obeys the Virasoro algebra, whereas the currents obey the Kac-Moody algebra, which is characterized by a central charge K, and the two-point correlation function is something like this, where Z is a complex coordinate in the 1 plus 1 dimensional plane, and K is an integer if I normalize things properly. Okay, so that's the basis of a lot of very beautiful work in mathematics and physics, these beautiful properties. Now, these properties don't generalize somewhat to higher dimensions, but are much more complicated. So for example, if I look at the two-point correlation function of a current, well, it has to be transverse because the current is conserved, and just by looking at the dimension of the current, which is always d minus 1, where d is this space-time dimension, this has to be modulus of momentum. And then you get a coefficient which is now another universal number, which is sort of analogous to this number k in lower dimension. So this is a number, but this is no longer an integer. We don't even know if it's irrational. Almost certainly it is. And in fact, our numerical, we have the corner Monte Carlo studies reported in our paper reports one of the best estimates of a value of this number for the Wilson-Fisher CFT.
This be any two currents, or is the energy current?
Or? No, this is some flavor current. You have some global symmetry. In this case, it would be O2, so it's the O2 current. So the stress energy tensor is, of course, different. Okay, so now it turns out if you apply the Kubo formula to this correlation function, you can show that this number, sigma of infinity, is the conductivity in units of the quantum unit of conductance. So it seems, so it's a very important quantity which can be measured, and so we are quite interested in knowing its value. And as defined, it's not so hard to determine. But as I'll show, and I don't know, I guess how I'm doing with time, this number is actually not really the conductivity. It's a certain high frequency property, and we'll come to that, of course. Okay, so another thing I'm going to need subsequently is not just the two-point correlation function of J, but also its OPE. And now there's an infinite number of terms on the right-hand side. This first term here is just this term written in a different language. So this is the OPE of two currents when you bring them close to each other. But what I've written it in frequency space by taking a Fourier transform in the limit of very large frequencies, which is like bringing them together to the same point in space-time. And so on the right-hand side, you find, of course, the two-point correlation term. And this term will be quite important. This O of P corresponds to some scalar operator, which is in fact the operator that tunes you away from this special point. It's the one relevant perturbation allowed in the CFT. And that has dimension less than the space-time dimension, where this 1 over nu is what physicists call the correlation exponent. And then there's some combination of stress energy tensors that in general is actually quite hard to write down. I've just taken particular component xx and worked it out. If you take the most general j mu, j nu, you get 157 terms here. And those are all have a very delicate structure which is constrained by conformal invariance. Okay. All right, so that's then a definition of the problem. We have this conformal field theory which can be realized in this Bose-Hubbard model, and these are some of the mathematical properties that are obeyed by this conformal field theory in its ground state. The analogous properties for CFT2s are very familiar to many mathematicians. The ones for CFT3s are almost nothing is rigorous, and so there has been some very nice mathematically rigorous quote-unquote work, so-called by the bootstrap method in the last few years, which I won't really say anything about. Okay, so now let's use this CFT data. This is how you characterize the CFT by the operators and the OPEs to do something. Okay, so this is the phase diagram I showed earlier. And so now what I'm going to do is turn on a temperature. So I'm going to take not the ground state, but some thermal Gibbs ensemble at a temperature T. So now what happens is that on either side of the critical point, which I won't say much about, you have these blue regions, and in those blue regions, the quasi-particle picture or its cousins pretty much work. So that's not my focus here, so I won't say anything about it. But what we're interested in is in this region in between, where you have this conformal field theory without quasi-particles, and its excitations are don't move in straight lines as little lumps. They can't be well separated. And it's described by this OPE that I've just discussed so far. Okay, so in principle anyway, the Boltzmann theory, you don't expect it to apply. But nevertheless, in this section, since we don't know how to do anything better, we're just going to apply it. There is certain limits for certain CFTs. You could imagine that the Boltzmann theory would work. Okay, so how does the Boltzmann theory work? This table is kind of going to make a description of the way things were and the new way we have to do things. In the Boltzmann theory, you first figure out the quasi-particles. You figure out how they interact with each other, and then you put everything in the Boltzmann equation, and you predict your favorite experiment. So let's try to do that here. So here, the way you do this is you generalize the CFT to one where there's an infinite number of components of this complex field psi. You go from the O2 model to ON model, and as n becomes large, this model becomes solvable and has quasi-particles at n equals infinity. So at large n, or for this weak, essentially free CFT3, if you compute the conductivity, this is what you get. So first of all, this is at finite temperature, and remember I told you the conductivity was sigma infinity, this number in the OPE of two currents. And that is the value, but it's the value at zero temperature. In other words, omega over t going to infinity. On the other hand, what's happening at omega over t going to zero is something very different. So here since this is a kind of a free CFT, when you raise it to finite temperature, you create some excitations which carry positive and negative charges. When you put an electric field, they move in opposite directions. And since it's free, they're able to move without collisions. And so you have essentially a perfect conductor. So there's a perfect conductivity with a delta function and a coefficient proportional to temperature, which measures how many excitations you have and how fast do they move. So now you put in some weak interactions, and you put in weak interactions from this psi fourth term. So remember this U star that characterizes Wilson-Fisher fixed point. And then you find in the Boltzmann approach that this delta function becomes a Lorentzian roughly, and you get a conductivity which in a sense is really large, and in fact goes to infinity as n goes to infinity, because that's when the interaction between the particles become weaker and weaker. So this is something you can compute then. So what you find, first of all, in the large n limit, this is just some number of order 1 plus 1 over n. And this, the DC, this is the actual conductivity, actually diverges as n goes to infinity. And this 0.523 comes from the solution of a Boltzmann equation. So now you have this very, first of all, you have a structure which is highly non-uniform in n. At large frequency, leading term is of order 1. At small frequency, it's of order n. And the width is of order 1 over n. So the n goes to infinity and the omega goes to 0. Limits don't commute. And so this is kind of all very delicate. But these are all, the whole function and everything is a property of the CFT. Previously, we learned about sigma of infinity and the OPE coefficients. But now we have a whole function with, coming out of a Boltzmann equation, which is a very strange thing for most conformal field theorists to encounter. Okay, so that's the result, the old result, and we're now going to try to think about it in other ways. Okay, so that was part 2. So when do I have to finish? Thank you, I forgot. 2:15?
Yeah.
Okay, I'm doing fine. All right, so now let's try something else. So this was the recipe we tried so far. We said assume they are quasiparticles, which really there aren't, but in some limit there are. But so now we want to, come to the 21st century and try something that really treats the conformal field theory on its own footing. So as I've already said, the things that characterize conformal field theory, the analog of quasiparticles are primary operators. And the analog of the scattering matrix elements, although you can't well separate the excitations, you can still talk about what happens in correlation functions when two of the excitations come close to each other. And that's the OPE. And so these OPE coefficients you can think of as the analog of the S matrix elements of the quasiparticle picture. So you want to use this information to compute the conductivity at finite temperature. Okay, well that's actually initially looks fairly straightforward. You just take the OPE. What happens when you take two currents at some frequency which is larger than this momentum p, but we're going to put the momentum p equal to 0. And just evaluate the expectation value of the left and the right of this equation at finite temperature. So this is just a number, so that just gives you sigma of infinity. Then this thermal operator, in fact, acquires an expectation value at finite temperature, and so does the energy momentum tensor. You heat something up, there's a finite energy density, and that's going to give you some non-zero expectation values there. So you just do that, a very simple type of analysis, and all of these coefficients you can, in principle, determine in a much more systematic way, either numerically or from 1 over n expansion than you could for the conductivity at finite temperature. So you do that, and you get an expansion like this. And now you see that this expansion actually only makes sense when omega is much bigger than t, because the higher order terms have higher and higher powers of t over omega. So this gives you the large frequency dependence of the conductivity with omega, but the low frequency conductivity, which is where the Boltzmann equation kicked in the limit of a free CFT, I can't say anything about. But anyway, so these are numbers you can then compute, and so this is pretty much under control. You can do it on Euclidean time, Minkowski time, basically the same sort of analysis, and you can work out. We've certainly worked out these terms, and maybe one more if you really worked hard.
The coefficients B1 and B2 are universal, or
they're all universal. They're all universal.
and they're known, or they're
Well, so they're known in the 1 over n expansion. In this paper, we computed a few of them, up to order 1 over n. And we also, as I show you in the next slide, there was numerics. So there's a bunch of other data. So numerically, some of those coefficients we know extremely well now. So this is the conductivity, but at imaginary frequencies. So we're working Euclidean time, where time is periodic with length 1 over temperature. And so these are the values of the conductivity as a function of omega over t. Now this, by just the fact that it's a function of omega over t is highly non-trivial. If you take the original lattice model, the conductivity is a function of frequency, and it depends on all the coupling constants. So it took many years of work by Erik Sorensen to finally have enough data in the scaling limit to really show convincingly that in the end that there was a regime where the conductivity was just a function of this integer n. So you could change the temperature, this curve won't change. You can do the simulation at different temperatures and you get the same value. So I'm not showing that here at all. And this is done on a model on a cubic lattice called Villain model, where you're just taking integer currents, which satisfy current conservation on every link, and just summing over all possible current loops with some weight, and that's it. It's a very simple model with only integers that you have to simulate. But anyway, so you get that's the data, and the blue line is a fit. And from the fit, you can then, for example, read off the value of nu, which is known from other people's work to be this value, and the agreement is really excellent. You get almost the same value of u up to 2 decimal places.